Hi, this is the preview lecture for lecture 16. So previously we have discussed about the derivation of drift-diffusion model from the Boltzmann transport equation. And from today we'll talk about how can we actually solve these equations. So now we have drift-diffusion model. We have to solve these 5 equations. The first one is the Poisson equation. Here, divergence of displacement vector, which can be written as permittivity multiplied by electric field. Once again, by adopting the electrostatic approximation, we can express it as gradient of our electrostatic potential. So you have seen this Poisson equation many times, and here you can identify two different quantities. One is hole density and electron density. Of course, we have another one. However, this is just doping density, which is a given constant at a given position. So now our goal is to solve the hole density and electron density to close this equation. For that purpose, we have to solve electron continuity and hole continuity equations. This one shows the electron continuity equation, and this one shows the hole continuity equation. As you can see here, so in terms of electron flux or hole flux, both continuity equations share the form. So time derivative of a certain carrier, electron or hole, can be written as minus divergence of carrier flux. However, depending on the polarity of this carrier, we can have different expressions. For example, if we have electron current density, then we have to multiply minus q to f sub n to have j sub n. Now we have positive 1 over q in front of this right hand side. On the other hand, in order to obtain j sub p, hole current density, we have to multiply just positive q to our hole flux. So that's the reason why we have here still minus 1 over q. So please don't be confused with these signs. And question still remains. In order to obtain the information about electron density, we have to solve the electron continuity equation. However, here we have a new vector called electron current density. How does it look like? It is shown here, and there are 4 electrons and holes. As you can see, these expressions contain 2 terms. The first one is directly proportional to the electric field, so this term is commonly called as the drift term. And the second term is related with gradient of our carrier. So this is diffusion phenomena. So this term is, the second term is called as the diffusion term. So when you have a look at j sub n and j sub p, you can find that they look almost the same. However, here you can see that the coefficient for diffusion terms are the opposite. That is the only difference between Jn and Jp expressions. So, in principle, when we talk about drift diffusion equation, we have to solve these 5 equations. So, however, for example, if we are talking about a unipolar device where the hole density is much smaller than electron density everywhere inside the device, then we can only solve electron continuity equation and consider only electron density in the source term of the Poisson equation. On the other hand, if we have much larger hole densities all over the device, then we can neglect electron density and consider only hole continuity equation. So you can easily understand this specialization. But in principle, we have to solve these 5 equations. So when you think about continuity equation and the expression for current density, then they can be merged because, here we have the explicit expression for J sub n, and it can be merged into the electron continuity equation. So when we just insert it, then we can have round n over round t is given by this expression. And in many cases, we are talking about steady state solution where every time derivative terms goes away. So then our task becomes drastically simplified. We can just solve divergence of this complicated expression should vanish. That is the combination of the electron continuity equation and the expression for electron current density. In today's lecture, I will think about 2 different structures like n plus n plus structure where we have heavily doped region and heavily doped region. In between, we have relatively lowly doped region. One is long device and one is a short device. The long device has the total length of 600 nanometer and short one has 10 times shorter length. So just 60 nanometer long. And here we have doping densities for highly doped region and lowly doped region, and they are just multiplied by a factor of 100 in 6 nanometer long version short device. So we have 5 times 10 to the 19, 2 times 17, 2 times 10 to the 17. Okay. So anyway, now our goal is to develop a code which can solve the coupled system of our Poisson equation and continuity equation. So we will just show it to you. We have to talk about boundary condition. So how can we consider the boundary condition? Where is the boundary? So since the device is still one-dimensional, and here we have one contact and other contact. Here we have heavily doped n plus region and also heavily doped n plus region, and here we have lightly doped n region. So here we have certain metal semiconductor contact and metal semiconductor contact, and these contacts are regarded as ohmic contact. So in this case, this ohmic metal always keep the position nearby the metal as a local equilibrium. So therefore, we can say that the electron density of that position should be the same with the doping density. Since in the long device, the doping density in the n plus region was 5 times 10 to the 19 per cubic centimeter. So we have to solve this expression. This expression just shows that electron density should be the doping density, n-type doping density. Simply we are solving this expression, then we will get the electrostatic potential which is satisfy this expression. So now as a solution of this expression, we will get the potential at equilibrium will look like this. So these two values, so values at the left contact and right contact will be fixed to predefined value given here, and for other points we will solve the equations. Of course, this specific value like 5 times 10 to the 17 per cubic centimeter is just specific for this long device. If we are considering short device which has just 60 nanometer long channel, then we will have just 5 times 10 to the 19 per cubic centimeter in order to calculate the electrostatic potential at the boundary point. Okay, so you can easily understand this modification. And as you know, we cannot directly dive into just drift-diffusion equation. So it's not possible. Simply you can try, but it is not successful. So the safe way is first solve nonlinear Poisson equation at equilibrium. It is almost always guaranteed that you can solve nonlinear Poisson equation without much difficulties. So I can guarantee that you can get this nonlinear Poisson equation solution. And only after that you can try the solution of drift-diffusion model. So in this slide, I'm just showing the code to solve the nonlinear Poisson equation. You have already solved it before, so I will just quickly sketch the equation, the implementation. Here we have delta x, and yes, we have 600, almost about 600 points, because we are now talking about 600 nanometer long structures, and these 2 points are just introduced to identify the doping boundary. And here you can see that the lowly doped region and highly doped region and highly doped region. So n don, this n number of donor density, that is just showing the doping density. And after that, the Jacobian matrix and residue vector are the same as before. Your calculation is just exactly same as before, and now you can get the full code. First, define certain variables, and first define your electrostatic potential by using local equilibrium condition. After that, just construct Jacobian matrix and residue vector and calculate the update vector. And when you repeat this procedure sufficiently long, then you will get the converged solution. So then you can plot it, and that is shown here for long structure. As you can see that, oh, here you have higher potential at n plus reason. So you know that this is corresponding to your n plus reason and n plus reason, and this is corresponding to your lightly doped n reason. So now you can see that for your n plus reason you have higher electrostatic potential. It is simply because at equilibrium your electron density is given by Ni times exponential phi over Vt. Okay, so now up to now we have not made any progress. We just repeat our previous work on nonlinear Poisson equation. And how about the next step? In this case, we will try to solve the continuity equation. So let's assume that the potential is fixed as before. Now the potential is just fixed, and you can solve just one continuity equation. Of course, you have also whole continuity equation, but for a while, just to neglect it because this device is purely n-doped device. So you have really small number of holes, so you can safely neglect them. Then, when just to consider only electron continuity equation combined with the expression for Jn, now you have this expression. One-dimensional derivative of this expression. This expression is corresponding to J sub n should becomes 0. Yes. And moreover, here we have mu sub n and d sub n. You know, this is the mobility and this is diffusion coefficient, and they are regarded as constant. And even further, we will assume the following relation, frequently called as Einstein relation. So d sub n and mu sub n are proportional, so we can just multiply the summary voltage. For example, it's like this. If your mobility is given by 1000 square centimeter per volt second, and let's assume that your summary voltage is just given by 25.85 millivolt, then according to this Einstein relation, then your d sub n will be just given as 25.85 square centimeter per second. Of course, if you have different numbers, and your d sub n will change accordingly. Yeah. So in order to solve this equation, we just integrate our equation over small box. We are quite familiar with this technique. So integration from left end of its control volume to right end of its control volume. Once again, we have a certain position xi and xi minus 1 and xi plus 1, and the control volume for this x sub I point is given by from xi minus 0.5 to xi plus 0.5. Okay, so then when we just integrate it, since our equation itself just looks like first derivative of j should vanish, and when we integrate it, then this one goes away, and now we have just difference of jn values evaluated at the upper bound and lower bound. That's it. So then how can you express our j sub n values at upper bound or lower bound? Simply, it has the electric field dependent term and the gradient of electron density dependent terms. So we can easily understand these terms like electric field or gradient of n can be treated as just first derivative quantities like minus d phi over dx or dn over dx, and they can be well defined at this midpoint. Okay, so since now we have xi and xi plus 1, and we have a potential defined at that point and another potential defined at that point, the gradient or first derivative can be well defined at the midpoint as just a slope between this and that. So this slope is corresponding to our d phi over dx. So now we easily understand although the Jn evaluated at upper bound is given by this complicated expression, but this one can be just approximated as phi I plus 1 minus phi I divided by delta x. Also, this dn over dx term can be expressed as ni plus 1 minus ni, i's position, divided by delta x. We can easily discretize them. Of course, here we have d sub n, which is quite annoying, but we can kick it out by adopting the Einstein relation. So instead of this dn, we can express it as Vt times mu n. Oh, now this drift term and diffusion term both share the mobility. So now we can pull out our mobility here, and this expression becomes even further simplified. So now when we discretize it, so we assume that all of these quantity is just constant over our entire simulation domain. So now difference between Jn and another Jn can be just obtained by the difference between these terms. So our equation now becomes n times d phi over dx minus thermal voltage multiplied by dn over dx. That is evaluated at upper bound once minus lower bound. Yes. And as I told you before, these first derivatives can be well approximated as just finite difference. And here we have a certain electron density at midpoint. Oh, that is a little bit confusing. So we know electron density defined at ith node, and also we know that the electron density defined at x sub I plus 1th node. We have concrete values for these 2 points, but we are now asked to provide the electron density at midpoint. How can you treat it? For a while, we'll just take average over these 2 surrounding grid points. We will improve this expression later, but for y, we will just treat it as just a simple average. Then now your expression can be really well calculated. Just to apply all of these expressions to here and here and here. Also same copies for xi minus 0.5 can be found easily, so you can replace this one, and this one. Then you have quite complicated expression, but anyhow you can calculate the Jacobian matrix. So please review these expressions. I will just upload the lecture material to our GitHub repository, so please visit it in order to get the lecture material. And yes, so yeah, so here we have notes, so you can just read it, yeah, and boundary conditions. So again, previously we solved the Poisson equation, therefore we needed to have the boundary values for electrostatic potential. Then now we are solving the electron continuity equation. In this case, we have to have the boundary values for electron density. However, for electron density, it is even more simpler. So previously we assumed that at metal and semiconductor contact, that point is just kept as a local equilibrium. Then now we have the doping density 5 times 10 to 17 for long structures, and that just given as boundary values for our electron density. That is quite simple. And if you are solving 60 nanometer long our short structure, then you have to apply 5 times 10 to the 19 per cubic centimeter as your boundary values. Okay. Then now let's go to the implementation. This code is based on the previous nonlinear Poisson equation solver. Simply it means that first apply your nonlinear Poisson solver. As a result of your nonlinear Poisson solver, you will have the electrostatic potential and calculated electron density. These values should be used as the initial guess. Okay, then now just to calculate the continuity equation, calculate the Jacobian matrix and residue vectors. So you can easily do it. After that, you can apply boundary conditions. So for example, here you are now saying that electron density of the leftmost position should be doping density, and electron density at rightmost position should be the doping density. That is the residue vector, and you can also calculate the Jacobian matrix. In this case, Jacobian should be diagonal 1. And yes, now you can solve the update vector and just to update your electron density with update. However, if you are doing it correctly, then your residue underscore elect itself should be very close to 0. Why? Because you are starting from the real solution. Therefore, your legis underscore elect should be quite small. So since this one is so small, your update would be also small. So you will have more or less almost identical electron density. Then here you have comparison for short device 60 nanometer long device. So please do it by yourself, and this one just shows a linear scale curve for electron density as a function of position, and in right side you can see that the electron density in logarithmic scale. So they are just showing the same quantity with linear scale and semi-logarithmic scale. That's it. So finally you have homework. So due is next Monday as usual. Today we have talked about how can you solve the NNN structure. In that case, we were able to solve only electron continuity equation. However, now we have to solve the p-n junction at equilibrium. So both p-n junction, p region and n region, the doping density is just 10 to the 17 per cubic centimeter. First, solve the nonlinear Poisson equation. You can do it quite easily. After that, just to solve the drift-diffusion equation, here when you say drift-diffusion equation, just to solve the continuity equation. As we did previously, since you have the solution, your residue should be quite small and your update should be quite small. Just to verify that you can solve this equation immediately once after you have the solution of a nonlinear Poisson equation. The only complication related with this homework number 14 is now you have to solve both of electron continuity and hole continuity, because p-n junction both contains electrons and holes, so it is not allowed to solve electron continuity only or hole continuity only. So please solve both of them, but anyhow, since the potential is fixed, then you can immediately get the solution. Okay, so okay, see you soon. Bye.